Imagine being able to run Windows, Linux, and macOS all at the same time on the same system, flipping back and forth between them with ease. I'm doing it right now thanks to hardware virtualization. But what exactly is virtualization and why does it matter to you? Because it's the magic that allows a single piece of hardware to host a multitude of systems all at the same time. We'll also delve into the realm of hypervisors, the code that orchestrates the symphony of virtual machines from the bare metal prowess of a Type 1 to the flexibility of a Type 2. And we won't stop at mere theory. I'll guide you through the practical magic of setting up Proxmox, a potent hypervisor that brings this virtualization to life. Watch as we conjure up Windows and Linux from the digital ether, running atop Proxmox with seamless agility. And for the grand finale, witness the spectacle of the full desktop macOS operating system running gracefully on an Intel server partition off in my closet. Hey, I'm Dave. Welcome to my shop. I'm Dave Plummer, a retired software engineer from Microsoft going back to the MS-DOS and Windows 95 days, and today we're going to explore virtualization. On my desk here in the studio, I've got a desktop Threadripper PC and a Mac Studio Ultra, and that's where I do the bulk of my coding, writing, and video editing. Behind the scenes, though, there are numerous other machines, like a Linux system that runs all of my LED lighting. There's also a Windows machine where I run the latest desktop bits like 23H2 so I can safely stay up to date on things, and a Mac where I run home automation, as well as a 420TB TrueNAS server. What's more impressive, though, is that all of these machines are really one machine, a storinator from 45 drives that features 30 14TB drives, 8 fast SSDs, 384GB of RAM, and a 16-core, 32-thread Xeon Silver CPU. But how is that possible? Well, it's all thanks to the magic of virtualization. All of those operating systems, from Windows to Mac to Linux, are running on the same hardware thanks to a layer known as a hypervisor. Each of these operating systems thinks it's running on its own computer, unaware that it's actually sharing the physical machine with others. This is possible through this special layer called the hypervisor. Think of the hypervisor as a kind of manager for the operating systems, which are known as virtual machines. The hypervisor's job is to divide the computer's resources like CPU, memory, and storage among the VMs. It's like having a single pizza, which represents the computer's resources, and the hypervisor is responsible for making sure that everyone gets a fair slice of pizza. There are two main types of hypervisors. Type 1. This is kind of like a strict, no-nonsense manager who works directly on the shop floor, which in this case is the computer's hardware. There's no middleman. This is more efficient because it's directly in touch with the hardware without any layers in between. It's used in environments where performance and reliability are critical, like in data centers. Proxmox and Windows Hyper-V are examples of Type 1 hypervisors. Type 2. This one is more like a friendly, approachable manager who works through a supervisor, which is the host operating system. It's software that you install on your operating system, and it manages VMs on top of that. It's easier to use and more common for personal use or development purposes. Virtual PC and VirtualBox and Parallels are examples of Type 2 hypervisors. The hypervisor also ensures that these VMs are isolated from each other, like giving each person their own personal space so they don't see or interfere with each other. This way, if one VM crashes, it doesn't affect or bring down the others. So in a nutshell, a hypervisor allows one computer to act as many, keeping each environment separate and managing them efficiently. It's a bit like having different people share a house without ever running into each other, each person with their own room and resources, living together but independently. Now remember, we're not talking about emulation, because when your code runs, it still runs on the real CPU and talks to the real memory, but it's all done under the careful administration of the hypervisor, which arbitrates which operating systems get access to which resources. Now you might think that this is going to add a layer of expense to everything, but remember that the hardware virtualization requires support directly in the CPU, and so the overhead for a Type 1 software hypervisor can be as little as 1%. On the storinator, I'm running Proxmox, which is based on a distribution of the Linux operating system that is specifically designed to operate as a Type 1 hypervisor. On top of Proxmox, I've installed multiple versions of Windows, Linux, and macOS. It also runs lightweight Linux containers. Let's take a look at how to set up Proxmox on a brand new system. I've got a bare bones PC and a USB stick with an install image for Proxmox, so let's see what's all involved in setting it up. As soon as we boot off the USB key, we're into the Proxmox installer, and we'll click Install to get rolling with the process. The installer will get rolling and we can see it requesting and receiving a DHCP address for our system. And then we're presented with a license agreement and a default disk. And we'll pick our time zone here as being Los Angeles. I'll type in a password and then confirm it. Notice my caps lock is on. That will come back to haunt me, I assure you, because I did not see it when it happened in the moment. We give the machine a local name. I'll call this one Hypervisor, if I can spell it correctly. And then finally, we are presented with a summary of all of our choices. When I click go, we'll just fast forward through the process here because like any operating system, it takes a little while to install. This will run through to 100% pretty quickly. That will all be followed by a reboot at 100%, which will take us back to the grub bootloader from which I will pick Proxmox, and then we'll boot into Proxmox itself. Now that we have Proxmox installed, we can create virtual machines where we can install individual operating systems, each of which will think and act as if it has exclusive access to the real machine. Note that it only sees the resources that we allow it to. For the CPU, that's easy. We just specify how many CPU cores the VM can use up to the number actually available on the hardware. And across all of the VMs, we can assign more cores in total than the CPU actually has, and the hypervisor will take care of sorting out how to allocate and rotate and share amongst them. Memory is a little more complicated. If you want to guarantee 8 GB of RAM to a virtual machine, you can do so, but that physical RAM will then be occupied and allocated to the VM whenever it's running and not available to the other VMs. What I often do instead then is to specify what's known as a ballooning limit on RAM. I might guarantee a VM 4 GB, but allow it to use up to a balloon limit of 16 GB. The 4 GB will be allocated to the VM the moment it starts, but the rest will only be consumed if and when the virtual machine needs and uses them. That means you can create VMs with much more physical total RAM than you actually have. Of course, if they all try to consume their maximum limit of RAM, there will be some contention, but it's still a great approach for unbalanced or peaky workloads. Hard disks are similar. You create a virtual disk in Proxmox, which is just a big regular file on the hypervisor side, but it appears as an IDE or SCSI drive within the VM. And you can under-provision the disk as well, meaning you can set an upper limit of 64 GB, let's say, but only the actual space used by the VM's operating system will consume any actual disk space on the host. As with RAM, this allows you to allocate more disk space in total than is actually present. I inadvertently tested this feature while researching this video by growing my own virtual disks to the point that they exceeded the space available. The VM was unable to satisfy the disk space request and was paused automatically by Proxmox until I resolved it by freeing up some space on the host, and then I was able to seamlessly resume the VM without a crash or data loss. So at this point, we have the hardware at the bottommost layer. Above that sits Proxmox, which is the Type 1 hypervisor. Above that sit the logical partitions that contain Windows, Mac, and Linux installations. Or they will, once we set them up. So let's install Windows so we can see what it's like to install an operating system on top of Proxmox. Now, because I have not installed an SSL cert, we have to proceed unsafely, and then we can enter our username and our password, which, wait for it, doesn't work. So I flail around for quite a while here trying to figure out what my password is and why it doesn't work. Eventually it comes to me that, oh, it's probably root with shift lock. And so I try that, and sure enough, 10th time we're in. I will brazenly dismiss the warning dialog that tells me I don't have a subscription yet, and that will drop us into the console where we can see our root machine, the hypervisor itself, and then any VMs, of which there are none yet. Now, to install any operating system pretty much, we're going to need an ISO image, so let me go and get the Windows 11 multi-language English version download. Let's see how long this will take to download. 60 seconds, even sped up, that seems fast. Nice to have fiber. Anyway, we then upload that ISO image, which also goes fast, mostly because I'm speeding up the video, but it's still pretty quick in real life too. Next, we create our VM. We'll call it Windows 11. We'll go in and specify that it is in fact the Windows operating system and give it the ISO image for the installer. We'll just pick the defaults of local storage for our EFI and TPM storage, and we'll give it, let's say, 16. Nah, let's be a little more generous. Let's go 24 GB. On the CPU side, we'll give it 8 cores, and then we'll give it 4 gigs. Nah, let's give it 8 gigs of memory. 8192. That'll do nicely. We'll accept the defaults for networking, which should make it work just fine. We'll check the box to start it automatically, and we'll let it churn away for a few seconds. And when we click on the console tab, we should get a base VGA representation of what's going on that system. It's now booting, coming up into Windows Installer, so we'll pick Install Now, and we'll let it run through and do a Windows install. I imagine you're all pretty familiar with this process by now, so I'll just pick my Windows 11 Pro and we'll pick custom install, get the files a copying, and let that run for a few moments until it is done installing all the files. And you might expect that after the install, it just reboots and comes back up in Windows 11 as you would hope, but it does not in my case. And the reason for that is that I edited the virtual disk, and so it fell out of the boot order. So when it comes back up, it's just going to come right back up into the Windows installer, pretty much no matter what I do. Once I figure that out, we'll go into the options and we'll drag IDE 0 up to be the top of the boot order and enable it. We'll disable the other one. Now, when it boots up, it should come up in Windows itself. And indeed, it does. When I'm given the options, I will pick, let's see, United States, English. Where's English? Oh, US first. Skip the keyboard layout edition. We don't need that. Just going to check for updates. There are no updates that it appears to care about, or it does it silently. Win11HV will be the name, and we'll let it spin through setup. Just cancel all these things, go through them, go down and turn off the tailored experience and advertising ID because I tend not to roll with those. With those checked, inking and typing is probably fine. We'll say accept. Don't you wish Windows installed this fast for real? Maybe one day it will. For now, let's go download CPU-Z so we can find out what's going on with our CPUs. We'll also start up Task Manager when I get a second here. Let's see, we'll put those side by side, switch this to multiprocessor view, and run the benchmark. Then we can see all the cores pegged. The numbers here aren't particularly impressive, but there are reasons for that, including the very limited resources we gave this machine and only 8 cores. As you can see, installing an operating system in a guest VM is very much like installing it on the bare hardware, and intentionally so. You can even press a key early in the boot sequence to edit the BIOS of the guest machine, but unlike a real machine, it's rarely required because you can configure most of the interesting things about it from the Proxmox UI. I noticed that CPU usage was high in the VM, up to 80% utilization of the 8 cores that I had allocated. I think that's actually normal for a fresh Windows installation, as OneDrive and the search indexer were busy doing all they could do to keep the machine in sync and properly indexed. If we go up to the actual hardware, however, which has 32 cores in total, we see that only about 16% of the machine's real compute power is being utilized. And that's, in part, the beauty of virtualization. You can share a scarce resource like CPU between multiple operating systems in order to take advantage of the hardware you do have. Now I've got a bit of a surprise, although I suspect a few of you might have seen this coming. You see, our real machine isn't a real machine at all. It's been Proxmox running within Proxmox, meaning it's turtles all the way down. Sort of a digital inception, but less confusing than the movie, let's say. This is all taking place on the Storinator, which runs Proxmox on the bare metal. Then under that is a virtual machine containing another Proxmox instance, and that is where we install our Windows operating system. Except perhaps for testing things, which is precisely what I was doing, you wouldn't normally run nested hypervisors in production on most hardware, but we've demonstrated that it's more than possible. Up at the root level of the machine, then, we have the 30 spinning disks, a half dozen SSDs, 384 gigs of RAM, and so on. Let's see how I allocate those resources to the 10 or so virtual machines that I have running on my Storinator. When I expand the Proxmox node, you'll see all of the VMs that I have installed underneath it, and below that you'll see 4 storage locations that are available to be shared by the various VMs. On the right-hand side, we see a details pane where I have a TrueNAS installation, Ubuntu, Windows 11, a Mac, Windows NT4, modern Windows Server, Windows 11 23H2, XP, and then the hypervisor setup that we were playing with earlier. If I pick the entry for the NT4 VM and then go into the console page, you'll see NT is in the midst of setup, so we'll let it churn away, and we'll take a look at Windows XP. This is a complete Windows XP installation, so we can see Task Manager. It's only got 4 cores allocated to this VM, so it shows up as 4 CPUs in the Windows Task Manager. And next, if we select Windows 23H2, we get Windows 23H2 running side by side with XP on the same hardware. And perhaps even more interesting, if we click on the Mac icon, we can see macOS ready to boot. So we'll press Enter. That will bring up the Apple icon. It'll turn away for a few moments, and we should be up and running on the Mac desktop shortly. As you can see, this is running a contemporary version of macOS, not some ancient old version. Once I enter my password, we should drop into the desktop proper. Let's have a look. macOS properly reports it as a Mac Pro with a Xeon 4216 Silver CPU, and it says 2.1 gigahertz, but that, of course, is the base rate. We also seem to have full internet working under VMXNet 3 Ethernet, which shows us connected and operating. Suffice to say, this is not a scenario that Apple encourages or supports. I've got enough dead and retired Intel Macs that I felt okay using one license in this form, but if you can see, you get into iMessage here and it's going to ask for your user ID and your Apple ID, and I'm not quite that bold. Cancel. Everything else seems to work properly. We can change our desktop. It takes effect immediately, and it's your full Mac desktop running inside a VM on an Intel server. Let's head back into the Proxmox console so I can take a look at TrueNAS and show you one of the other systems that's running actively on this machine. TrueNAS is, as the name implies, a network-attached storage system. And so we'll go to my TrueNAS link, we'll type in my admin password, we'll log in, and here we can see that the machine is up and running, has 32 cores, 125 gigabytes of active RAM. Storage, everything looks healthy right now, the network is running, the pool is up, everything is running happily. My most important VM contains a TrueNAS scale installation. TrueNAS will be responsible for managing all of the ZFS pools across those 30 hard drives, and it loves to have a lot of RAM available for caching. To that end, then, I've allocated 128 gigabytes of RAM right off the top exclusively for TrueNAS. There's no ballooning memory here, it gets all 128 gigs right from the start. What about the disks, though? Well, Proxmox does allow you to pass a disk along exclusively to a guest operating system, but 30 disks would be a lot to manage. So what I did instead was to take advantage of Proxmox's PCI device pass-through. In the hardware configuration for Proxmox, you can see a list of 8 PCI devices from the host that I am passing directly through. 2 of these are the Broadcom HBAs or host bus adapters that connect to those 30 drives. By passing through the 2 adapters, all 30 drives will be under the exclusive control of TrueNAS. The HBAs will appear to the TrueNAS operating system as if they are natively attached to whatever hardware it believes it's running on, and I/O will run at its full speed. When a piece of hardware is passed through to a VM, normally that means that only that one VM will have access to the hardware, and its access will be exclusive. In some cases, as with network cards that have multiple ports, you might pass along only a part of the device, such as a single port. But in most cases, you'll be passing through the entire PCIe card. TrueNAS has no knowledge of any of this, of course. As far as it knows, it's running on a dedicated Xeon box with 128 gigabytes of memory and 30 hard drives connected via 2 HBAs. It has no idea that other operating systems are running alongside of it, and no way to check. Proxmox provides a great deal of protection in the disaster recovery space because you can snapshot and back up VMs both on demand and on a regularly scheduled basis. A VM can be restored back to its prior snapshot with a single click, and the entire machine state, including its hard disks, can be restored as needed. One time I trashed the Proxmox config so badly that I couldn't get the machine on the network at all. I fought with it for a day before deciding to revert to a backup, and then it turned out that my backup could not be restored. I thought all was lost, but I simply did a fresh install of Proxmox and then restored the VMs from backup, and I was up and running again within the hour. Using virtualization is a great way to test drive new applications and even operating systems. If you want to experiment with it on your own, there are 2 approaches you can take, and both are free, presuming you already own Windows. The first approach is to take a bare machine and install Proxmox on it, and then set up your virtual machines. The other is to enable the Hyper-V feature within Windows, which allows you to create virtual machines that run seamlessly alongside your Windows installation. In fact, even though it feels like a Type 2 hypervisor because you install it as part of Windows, it actually installs underneath Windows and acts as a Type 1. In theory, you could even run Proxmox under Hyper-V and experiment with it under Windows. And by this point, you might be wondering where WSL2 and the Linux subsystem fit in. WSL2 integrates Linux into Windows by using a lightweight VM that contains a real Linux kernel. This VM runs on the Windows Hypervisor platform, which allows it to operate efficiently with about 1 to 2% very minimal overhead. The Linux kernel in WSL2 has been optimized by Microsoft to be fully compatible with the Windows environment. This means that while WSL2 does virtualize hardware resources, it's designed to do so in a way that is seamless and efficient, providing performance that is very close to running Linux natively on the hardware. The interaction between Linux and Windows in WSL2 is thus a hybrid model. It allows for direct system call translation between the Windows NT kernel and the Linux kernel, which is facilitated by the virtualization layer and the Windows subsystem model. This enables a high degree of interoperability, such as accessing the Windows file system directly from within Linux and vice versa, that would not be possible in a straight hypervisor model. If you found today's episode to be any combination of interesting or informative, I'd be honored if you'd consider subscribing to my channel, which in turn will encourage the production of more episodes like this one. And if you have any interest in matters related to autism, Asperger's, or ASD, please check out the free sample of my book on Amazon, Secrets of the Autistic Millionaire. It's got nothing to do with money and everything to do with living a successful life on the spectrum, however you define it. It's everything I know about the spectrum now that I wish I'd known way back then. Thanks for joining me out in the shop today. In the meantime and in between time, hope to see you next time, right here in Dave's Garage.